Hi, and welcome to 10.5a Electric Fields 1. In this lesson, students will be able to calculate the electric field strength at a given point near an electrically charged sphere. And just a preview into the next lesson, that's when we're going to do something called like electric field lines as a model to represent the electric field. I like to start by showing you the equation for the electric field strength and kind of a general idea of what an electric field is before we use that model to describe the electric fields. So let's start by talking about some new vocabulary. So we're going to have two different charges, just like we had with Coulomb's law, like Q1 and Q2. But now there's going to be a source charge, which we'll use a capital Q, and that's going to be the object causing the electrostatic force on other objects. Then we'll have a very small test charge, Q naught, and that Q naught is the object that feels the force of the source charge. By convention, test charges are positive. So we're going to use a positive test charge to determine the magnitude and direction of the source charge. How strong is the electrostatic field that the source charge is creating? So let's say you have a negatively charged source charge. What direction would a positive test charge travel if placed near that negatively charged source charge? Pause the video, think about it. Where is this going to go? It gets attracted to the source charge, okay? Because we're using, by convention, a positive test charge always. And what direction would a test charge travel if placed near a positively charged source charge? It would be pushed away. It would be repelled by that source charge. So by convention, we're using a positive test charge. So the way we describe or measure how the source charge is affecting the region around it is by measuring the electric field strength or the electric field intensity. An electric field is a region where an electrostatic force on a positive test charge can be detected. The strength of the field is a vector quantity. It has a magnitude and direction. The units for electric field strength are newtons per coulomb, and the equation looks like this. It's the electric field strength is equal to the electrostatic force divided by the charge, which is where we get the units newtons per coulomb from. Okay? So the way I like to, so that's the equation, right? Great, we could use the equation. I want you to start thinking about what the electric field actually is. If we have a source charge here, and it's a three-dimensional sphere, okay, that is going to affect the electric field around it, right? And it's going to be stronger when it's closer to the sphere, and it gets weaker as you go out in 3 dimensions. So think of this as like a 3-dimensional, maybe this is a glowing ball. And if it's glowing, then the brightness of the light is like the strength of the field. And it emanates out in 3 dimensions. So it's very bright. It's very strong when you're close to the sphere. And then the further you go out, it gets weaker in 3 dimensions. Okay, so we're having a visual of what that looks like. Sometimes I'll use this analogy. Let's say you have a stinky diaper. You know there's a stinky diaper somewhere in the room. And here's our stinky diaper right here. Okay, if I'm over here, I'm not going to smell it as much as if I'm over here. I can detect where that stinky field is. It gets more intense the closer you get in all 3 dimensions. So the smelliness is like the strength of the electric field. All right, but that's not really, I mean, and then plus now we're adding in the fact, okay, what if it's a positive test charge, which it should be by convention, and then what if it's a positive source charge? What if it's a negative source charge? So this, I would say, was repulsive all the time. But if you have a positive test charge and a positive source charge, let's try to imagine what the field looks like around the source charge. Might look something like this, where again the color intensity is like the strength of the field. And what direction will the source charge go? It's going to be pushed away. The cool thing about electrostatics is you have positive charges and you have negative charges. So if you have a negative source charge, you still have this electric field, but it behaves in the opposite direction. This positive test charge is going to be attracted to, and the closer it gets, the more intense the field is in all three dimensions. And this is why I like to introduce the concept and the equation of the electric field before we do the electric field lines, because I think I like this picture of the electric field because it gets the point across that it's in all three dimensions in a smooth region around the source charge. But tomorrow we're going to draw electric field lines as a model to represent the direction of the electric field. So this is like a little sneak preview. And the reason like it's a pretty decent model is, yes, it's showing the direction of the field with the arrows, but the whole idea is the closer the lines are to each other, the stronger the field is. And the further apart the lines are, the weaker the field is. So that's good, but then I have students who think that the electric field is only on the line that I just drew. The line is a model to represent this more nuanced thing that I use, like the light emanating from the source charge to represent. It's a region around the source charge. That's the electric field. So where is the formula for the electric field strength? It's going to be on page 4. So this is the one they give you in the reference table, but I like to think of it a different way. I mean, this is good. This will tell you how many newtons, let's say it's 500, the electric field strength is equal to 500 newtons per coulomb. That means that at a position around a source charge, let's say it's over here, that position, you don't actually need an object there. You're just describing that point in the region, and you're saying if you placed 1 coulomb of charge at that point, you would feel 500 newtons of force. Now, what direction am I going to draw my force vector? It's going to be away because by convention, we're drawing the electric field where a positive test charge would go. So yes, this is 500 newtons for every 1 coulomb of charge that you place at this specific point in the field. That's how that unit works out. That's how the equation, that's what they're showing you. How much force per 1 coulomb of charge are you feeling? But I don't know, if I'm describing the electric field strength based on the source charge, I want to know what is the charge of the source charge? Don't tell me how many units of force per 1 coulomb of charge that you would place theoretically at that point. Like, what is the magnitude of that source charge, and how far away is that point from the source charge that you're trying to measure? What is the field strength at that point? Doesn't that kind of make sense to me? Like, what is the source charge and how far away are we talking? That to me is like, okay, that is what the strength of the field is. So let's see if we could get an equation from this that is in terms of the source charge and the distance from the source charge. So let's consider a positive test charge being brought near a metal sphere with charge Q. We don't know if it's positive or negative, that doesn't matter. If we plug in the formula for the electrostatic force, we get this mess, because Coulomb's law says that it's equal to K Q1 Q2 over R squared. Here's Q1, here's Q2. Okay, so right now we do have an electric field strength equation in terms of the source charge and the distance from the source charge, which is what we kind of wanted, right? Like, what is the magnitude of this? If it's more charge, then it's going to be a stronger field. And how far away are we? If we're close, it's going to be a stronger field. But we have all this other mess. Let's try to get rid of this other mess. Let's see what we could do. We're going to multiply the numerator and denominator by r squared so that that cancels out. Then we're left with k, the source charge, times the test charge, divided by r squared times the test charge. As you can see, the test charge cancel out. And look at that. We're left with an equation for the electric field strength in terms of the source charge and the distance from the source charge. So this is a valid equation that you can use that's not on your reference table. And don't forget, you have to also include the electrostatic constant because we're talking about the strength, the force that's being felt. Cool. So I would recommend writing that formula in your reference table if you have it printed out there. All right. And let's see. So this is defining the electric field strength can be measured by the amount of force felt by 1 coulomb of charge at a point in an electric field. How much force would 1 coulomb of charge feel at that point? Or you could think of it as the electric field strength is directly proportional to the charge of the source and inversely proportional to the square of the distance from the source. And again, this is because it's emanating out in a spherical shape. It's another inverse square law. And also remember, the direction depends on where a positive test charge would go. So it's a vector quantity. It has a direction. So you could say the electric field is away from the source charge, or you could say the electric field is pointing towards the source charge. So sometimes they'll throw some graphs at you. How are the electrostatic force and the electric field strength related to r, the distance between the two charges? So pause the video here and try to think, what are these graphs going to look like? So it's an inverse square relationship there. And then, oh man, where is r over here? Well, it's directly related to the force. So that means it's going to be the same graph. But if you wanted to find an equation that relates E and R, we'd have to look at the equation that we just derived. And now you can see it's an inverse square law as well. How are the electrostatic force and the electric field strength related to the charge? So you could see for this first graph, pause the video and think about it. For this first graph, it looks like it's a direct relationship. For the second graph, does it look like an inverse relationship? I don't know. Remember, because when we were defining and deriving this equation, we were talking about two different Q's. So which Q are we talking about here? This is not the source charge. This is the charge that you place in the field. So if it's a proton, you're going to plug this in over here. If they say, let's say it's not a test charge anymore. Let's say that it's another sphere. All right, and you know the sphere's charge is maybe it's 5 coulombs. And they say, oh, you feel a force of whatever it is. The electrostatic force is 20 newtons. Okay, you plug in this charge, the charge that's in the field of the source charge. That's what you're plugging in over here. Okay, but remember, this is not affecting the source charge or the field itself. So how is the electric field strength of this source charge related to the source charge? It's not an inverse relationship, it's a direct relationship, because as the source charge increases, the electric field strength should increase, right? If we have a bigger charge now, I'm just going to make it the size bigger. Wow, look at all this charge. I'm building up a lot of positive charge here. I could feel the field is getting much stronger. I'm feeling more newtons per coulomb of charge that I would place in that field. Hopefully that makes sense. It's always a little confusing with like the Q and the Q, especially because they only give you this Q in the reference table. But that's the idea. So let's do an example problem that says a proton is placed near a negatively charged metal sphere. The sphere exerts an electrostatic force of magnitude negative 3.52 times 10 to the negative 18 newtons on the charge. What is the magnitude and direction of the electric field intensity at this location? So we'll write down the given information, and this is a piece of given information. The proton has a charge of 1.6 times 10 to the negative 19 coulombs. All right, that's E, that's the elementary charge. We know that. The sphere exerts an electrostatic force of, okay, so this is the electrostatic force. Interesting, negative 3.52 times 10 to the negative 18 newtons. And we want to know what is the electric field intensity. So you plug in, you write your equation. We're just plugging in numbers at this point. Easy peasy, right? Yeah. Times 10 to the negative 18 newtons per, right now it's 1.6 times 10 to the negative 19 coulombs of charge. But when we do this division, we'll have an answer in terms of newtons per 1 coulomb of charge. That would describe that position. So when you do the division, you get negative 22 newtons per coulomb. And notice it's a positive charge here. And we end up getting a negative number because the force was described as negative. It's an attractive force. All right, so we get a field that's pointed in this direction, attracted to it. So even though this proton is feeling this much force, if you were describing the field at that position, ignore the proton, you could describe this source charge by saying, at that position in the field, the strength of the field is negative 22 newtons per coulomb. If you put 1 coulomb of charge there, you would feel a force of attraction of 22 newtons. We're describing the field. We happen to have a source charge, a test charge there in the form of a proton. Something to note about the direction of the field and like when you're using this equation. If it was an electron, let's say the problem wants you to put an electron there, you would get an answer of, oh, well, actually, let's keep the source charge negative. We're just changing this test charge now. And if the problem flipped the fact that it was an electron and wanted to keep the source charge the same, let's try to get to the same exact answer, right? We're describing this same thing. Then this, would it feel attracted or repelled? It would feel a positive force. It would feel a positive force. It would be repelled. So it still works out to be the same magnitude and direction. You have a negative 22 newtons per coulomb. The direction of the field is still the same. We're just putting a different thing in the field, and it feels a different force. But the field strength is independent of what you place in the field. You're just measuring the strength of the source charge and how it's affecting the electric field around itself. Example 2, a proton is placed 2.5 times 10 to the negative 3 meters away from a metal sphere with a charge of positive 1.5 coulombs. What is the magnitude and direction of the electric field strength at this location? This one's a little bit different. Pause the video and see if you can figure out how to do it. So now it's giving us two different charges. It tells us that it's a proton, so that's 1.6 times 10 to the negative 19 coulombs. And it's telling us the source charge is positive 1.5 coulombs, and they want to know what is the electric field strength provided by this source charge. You could, let's see. Oh, they also tell you the distance is 2.5 times 10 to the negative 3 meters. That's important. So if you wanted to use the equation in the reference table, you'd have to calculate what the electrostatic force is first. And we do that using Coulomb's law. And you get 5.39 times 10 to the negative 4 newtons. So now we could plug that in over here. But what are we going to plug in for this Q? Well, we feel this much force if we put this at the location, right? This proton is feeling that much force. So we need to put the charge of whatever the test charge is, whatever the charge of the object in the field is, not the source charge. All right, so this much charge feels this much force. So what is the field intensity? I got 3.37 times 10 to the 15 newtons per coulomb. That is a pretty substantial electric field intensity. Let's see. This is a good amount of charge there, 1.5 coulombs. And this is 2.5 millimeters. So not only is it a pretty decent charge, but we're pretty close to that metal sphere. So it would make sense that the field intensity is pretty strong at that position. Let's see if we could use our other equation that we came up with, right? Because we know what the source charge is, and we know how far away we're talking. So let's use that other version of the electric field strength formula. The electrostatic constant times the source charge divided by the radius squared. So when you plug in your numbers, we can predict that, yeah, it's going to be a large number. We have a 10 to the 9 over on the numerator and a 10 to the negative 3 that's being squared in the denominator. So that leads to a pretty substantial magnitude. And I got a different number, so I must have maybe I jacked something up. 2.157, so that's 2.16 times 10 to the 15 newtons per coulomb. Let's see, that's the same power of 10, so I must be close. I actually just redid my force, and I got a different force. It should have been 3.45 times 10 to the negative 4 newtons. So those of you who are staring at your screen saying, no, it's the wrong force. It should be 2.16 times 10 to the 15 newtons per coulomb. Yeah, that is correct. I'm going to leave that little mistake in there because I just want to show you that sometimes people make mistakes, and that's okay. You want to check your work, see, and then do the work again if you need to. If you see something that's wrong, double check and learn from your mistakes. And my mistake was I went back in my calculator and I misclicked on this little 0.5. So if you're wondering why I was a little bit off, when I plugged it in the calculator, it didn't register the 5. It just is 2 times 10 to the negative 3. Anyway, that's about it. Thanks for watching and have a great day.